balloons. For a long time, scientists assumed that, like kites, ballooning spiders can fly because their silken threads generate enough lift to ride currents of air. But according to a study published in Current Biology this week by researchers at the University of Bristol in the UK, they don't actually need a breeze at all. It turns out spiders can fly using the electricity in our atmosphere.
Permanent Magnet Motor Technology, PM for short, has been introduced in several ranges of Rolls-Royce marine equipment. The PM motor consists of two main parts: a stator that carries a number of electrical coil windings, and a rotor fitted with a number of very strong permanent magnets. A rotating magnetic field is created by the stator, which interacts with the fields of the permanent magnets on the rotor. This generates a force which drags the rotor round, providing mechanical power. PM opens the way for innovation in
Hey guys, I'm just out looking for satellites and can never seem to see any. Everything that we're told through the media tells us that we're surrounded by them and they're all out in space. But, you know, as I've kind of been on this journey of trying to figure out how far away the moon is, seeming that it's closer than we're told, I would think that we would be able to see satellites whizzing between us and the moon at a constant rate. You know, all the pictures that you Google or whatever server you use, you bring up, shows you that there's all these satellites out there and that we're surrounded by them, and so we should be able to see them. But what I think is the reason we can't see them is because they're inside of the Earth's atmosphere. The moon is much closer than we're told, and makes me question, what space is in general. So, satellites, if they are real, are they just turbine driven free energy engines that are inside the Earth's atmosphere? I don't know. They look like them. They look like turbines.
The coolest idea I've heard recently for ion engines is the idea of an air-breathing engine under development by the European Space Agency. Instead of carrying any propellant at all, engineers at ESA demonstrated that a spacecraft in low Earth orbit should be able to pull in molecules of air right from the atmosphere and then ionize them and blast them back out. Since the spacecraft would be using unlimited solar electricity for power and pulling its propellant from the atmosphere, it could operate without refueling essentially forever. Spacecraft could operate at lower altitudes, and space stations could remain in low Earth orbit indefinitely without needing to be reboosted. It's going to be a real game changer. People always ask me why we're stuck with chemical rockets. Seriously, exploding a bunch of hydrogen or kerosene is the best that we can do? Good news! There are other exotic science fiction sounding propulsion systems out there which use electromagnetic fields to accelerate atoms, allowing their spacecraft to accelerate for months at a time. I'm talking about ion engines, of course, and several spacecraft have already used these exotic thrusters to perform some of the most amazing missions in the exploration of the solar system. There are other ways ion thrusters can be scaled up. NASA is testing a high-thrust version of ion engines known as the X3 Hall thruster. This engine is capable of blasting out ions and produces 5.4 newtons of force. Again, not much, but remember that previous thrusters top out in the thousands of newtons. I said that ion engines produce very little thrust, but there are some ideas to boost their output. The first is dramatically increase the amount of electricity that you're using to accelerate the ions. Instead of solar panels, NASA considered creating an ion engine powered by a nuclear reactor.
Greatest machines that push air is the jet engine. Jet engines suck air in the front and push a jet of air out the back. That force is called thrust, and it moves an airplane through the sky. Let's see how it works. A big fan at the front of the engine pulls air around the engine and sucks air into the core. We'll come back to that outside air in a moment. For now, let's follow the air in the core. It goes into a compressor, something like many household fans joined together. Each fan gets smaller and smaller as the blades squeeze the air into a tighter and tighter space, compressing the air like you would squeeze a balloon. The turbine is like a windmill that scoops up energy from the heated air and spins the shaft connected to the fan at the front of the engine. The excess hot air from the combustor blows out the back of the engine, producing thrust. Remember that air rushing outside the engine core? Together, the turbine and fan push a larger mass of air than the core ever can, for much more thrust. But that extra air passing around the engine core works more efficiently if it moves more slowly than the hot air rushing out the combustor and the back of the engine.
The coolest idea I've heard recently for ion engines is the idea of an air-breathing engine under development by the European Space Agency. Instead of carrying any propellant at all, engineers at ESA demonstrated that a spacecraft in low Earth orbit should be able to pull in molecules of air right from the atmosphere and then ionize them and blast them back out. Since the spacecraft would be using unlimited solar electricity for power and pulling its propellant from the atmosphere, it could operate without refueling essentially forever. Spacecraft could operate at lower altitudes, and space stations could remain in low Earth orbit indefinitely without needing to be reboosted. It's going to be a real game changer. A 550 metric ton Falcon Heavy is carrying almost 400 tons of fuel and oxidizer. The first stage will only burn for 162 seconds, and the second stage will fire for 397 seconds. That gives you a total burn time of about 9.5 minutes. Want to make some maneuvers? Want to accelerate for days, weeks, or even months? Too bad, you are out of fuel. Of course, these shortcomings from chemical rockets have led scientists to search for other forms of propulsion, especially when you're out in space, and one of the most successful so far is the ion thruster. When you're working out the rocket equation, an important factor is the velocity that you're ejecting your propellant. The most efficient chemical rocket can throw hot gases out the back at 5 kilometers per second. Ion engines, on the other hand, can eject individual atoms 90 kilometers a second. This high velocity gives the spacecraft a much more efficient acceleration. The best chemical rockets see a fuel efficiency of about 35%, while ion engines see an efficiency of 90%. So how do ion thrusters work? It's actually pretty weird and totally sounds like science fiction. Instead of hot gases, ion thrusters eject ions, which are atoms or molecules which have an electrical charge because they've lost or gained an electron. In the case of an ion engine, they're emitting positively charged ions which have lost an electron. Once you've got ions, you can direct them with a magnetic field, accelerating them into space at tremendous speeds. So where do they get all the ions? The thrusters create them by generating a plasma inside the spacecraft, and they bombard neutral propellant atoms of some gas like xenon with electrons. These collisions release even more electrons from the propellant, turning them into positively charged ions. This plasma soup of electrons and positively charged ions has an overall neutral charge. The electrons are held in the chamber, leading to more ionizing events, while the positive ions are siphoned out through a grid at the end of the chamber. As they pass through this grid, high voltage accelerates them out the back of the spacecraft at speeds of up to 90 kilometers per second. For each ionized particle that the spacecraft can kick out, it gets a tiny kick in return. The whole system is powered by solar panels, so the spacecraft itself doesn't need to carry any kind of battery or power system, minimizing the total weight that it has to carry. The big problem is that the kick really is tiny. The thrust of ion engines is measured in millinewtons, like thousandths of a newton. Hold a piece of paper in your hand. That's the kind of forces involved. But they can operate for days, weeks, even months, accelerating and accelerating long after chemical rockets would have run out of fuel. So if you're already out of the gravity well of a planet, they're very efficient engines for dramatic changes in velocity. NASA and other space agencies have actually used ion engines very successfully in a range of missions. They've been developing this thruster concept for decades, but were never willing to risk it on an active mission where a failure could end it. So NASA gathered up a bunch of these risky technologies and packaged them together as the Deep Space One mission, which launched in 1998. Deep Space One was equipped with 12 different technologies that NASA wanted to test out, including low-power electronics, solar concentrator arrays, various scientific instruments, and a solar electric propulsion system.
Guess what? Guess what is a big secret? Air traffic control towers are harvesting free energy. just like the towers that were used and squashed, but they weren't. They're being used today. Energy is free. Energy is being harvested out of the atmosphere. Airports are designed just like motherboards. They're designed to harvest free energy. Creating the frequency needed for their turbines to work. Runways are set up in very specific directions to harvest that frequency needed. They need this intake, they need this compression, they need this resonation, but they do not need fuel. They do not fly with liquid fuel. That's one of the big secrets. They tell us they fill all these airplane wings, jet wings, with all that fuel. And right here they show you it's air. Air. These chokers. And why would they be fueling a wing up into it from the bottom? That makes no sense. Liquid falls. You know, what? He has sunglasses on here. No eye protection, no arm protection. All this fuel being pumped into this wing, supposedly. Not protecting himself at all. Meanwhile, right back here, they're telling you it's air. It's air that is flying these planes. Compression. You know, the cabin compresses so the plane can levitate. That's the real zero gravity. So, if they've hoaxed us about 9/11 and hoaxed us about jet fuel, all this fuel being in the wings, if that's not possible, if jets fly on free energy, it proves that 9/11 was staged. If that's not jet fuel burning, because jets don't use fuel, "9/11's busted." Free energy is the big secret.
suck air in the front and push a jet of air out the back. That force is called thrust, and it moves an airplane through the sky. Let's see how it works. A big fan at the front of the engine pulls air around the engine and sucks air into the core. We'll come back to that outside air in a moment. For now, let's follow the air in the core. It goes into a compressor, something like many household fans joined together. Each fan gets smaller and smaller as the blades squeeze the air into a tighter and tighter space, compressing the air like you would squeeze a balloon, until that squeezed air is mixed with jet fuel, a kind of super gasoline. In the combustor, that air and fuel mixture meets a flame and shoots out the back of the engine. The rush of hot air spins a turbine. The turbine is like a windmill that scoops up energy from the heated air and spins the shaft connected to the fan at the front of the engine. The excess hot air from the combustor blows out the back of the engine, producing thrust.
flying animals, what do you think of? Birds, butterflies, or bees might first come to mind. But what about spiders? Even though they don't have wings, it turns out that spiders are actually some of nature's best aviators. So, how do spiders take to the skies? Lightning storms are one of nature's most powerful displays of Earth's electricity. But even under normal weather conditions, electricity is all around us. The atmosphere holds a positive electric charge, while Earth's surface holds a negative charge. Just like with magnets, similar charges repel away from each other, and opposite charges attract. This interaction creates something called an electric field. The force of this electric field is what allows for some spiders to defy gravity in a remarkable behavior called ballooning. It typically begins at high, pointy areas where the Earth's electric field is the strongest. First, a spider drops an anchor silk to secure itself. Then, it raises its two front legs in the air and uses special fine hairs to sense wind and electrical conditions. Sort of like a built-in weather station. If the conditions are right, the spider then tiptoes on its back legs, raises its abdomen, and releases its silk to the air. The silk strands are charged, which causes them to repel away from each other rather than tangling. This form of static electricity is just like what happens to your hair after rubbing it with a balloon. Now, ready to set sail, the spider breaks off its anchor line and lifts into the air using the force it gains from the electric field and wind. Once airborne, spiders likely use their legs to balance or control speed during their dangerous journey. Most of these trips are short, but some can last for thousands of miles.
Sometimes scientists assume that, like kites, ballooning spiders can fly because their silken threads generate enough lift to ride currents of air. But according to a study published in Current Biology this week by researchers at the University of Bristol in the UK, they don't actually need a breeze at all. It turns out spiders can fly using the electricity in our atmosphere.
The mystery of how spiders can fly for thousands of miles even in the complete absence of wind has finally been solved. Sometimes, when it rains or when they feel the urge to migrate, spiders get out their little silk knapsacks and balloon away. This ballooning behavior is well understood by spider scientists, but researchers have recently discovered that electric fields can not only trigger the behavior, but also provide lift. The latest research shows arachnids can make use of electrostatic charges in the atmosphere to power their journeys. This force, known as the E-field, can be detected by many insects and is used by honeybees to communicate with a hive. They travel via the atmospheric potential gradient, an electric circuit between Earth and the ionosphere, the part of Earth's upper atmosphere that's ionized by solar radiation. Sensory hairs called trichobothria found on the surface of the spider's exoskeletons move in response to electric fields. This suggested spiders can feel the charge in the air using the same sensory hairs used to detect a breeze. Many spiders balloon using multiple strands of silk that splay out in a fan-like shape, which suggests that there must be a repelling electrostatic force involved.
For a long time, scientists assumed that, like kites, ballooning spiders can fly because their silken threads generate enough lift to ride currents of air. But according to a study published in Current Biology this week by researchers at the University of Bristol in the UK, they don't actually need to breathe at all. It turns out spiders can fly using the electricity in our atmosphere.